Hi guys, so we'll be discussing two of the examples from chapter 7. The first example is this. Two copper conducting wires are separated by an insulating oxide layer. Modeling the oxide layer as a square barrier of height 10 electron volts, estimate the transmission coefficient for penetration by 7 electron volts. Electrons. A, if the layer thickness is 5 nanometers, and B, if the layer thickness is 1 nanometers. So first of all, we can see that the square barrier of height, which is also U, is 10 electron volts, which is greater than E, which is 7 electron volts. And with this, we can go here in the chapter, which tells us that when E is less than U, then we use this equation of alpha equals to the square root of 2m times U minus E, because U is greater than E, over H bar, and insert that into this formula for transmission coefficient. So that's what we did here. So alpha is equals to the square root of 2me, since we're dealing with electrons, and times U minus E, which is 3, divided by H bar, and we get this as our answer. So then, with our transmission coefficient given, we just change the value of L to Armstrong, because our answer in alpha was in Armstrong, so that they can cancel out and we can get our transmission coefficient. So for 5 nanometers, we get T equals to 0.963 times 10 to the negative 38. And for 1 nanometers, we get T equals to 0.657 times 10 to the negative 7. So we can see that reducing the layer thickness by a factor of 5 enhances the likelihood of penetration by nearly 31 orders of magnitude. Next, we look at 7.2, and the question states a 1.0 milliamperes current of electrons in one of the wires of example 7.1 is incident on the oxide layer. How much of this current passes through the layer to the adjacent wire if the electron energy is 7 electron volts and the layer thickness is 1 nanometers? What becomes of the remaining current? So we know that each electron carries a charge of E equals to 1.6 times 10 to the negative 19 coulombs. So we're given 1 milliamperes and we want to change it to electrons per second. So to do that, we divide that by the charge of an electron, and we get 6.25 times 10 to the 15 electrons per second, which is impinging on the barrier. So we use our T equals to 0.657 times 10 to the negative 7 from the answer we got in example 1. And we multiplied this by electrons per second. So this gives us 4.11 times 10 to the 8 electrons per second. And we want to change this back to amperes. So we multiply that again by 1.6 times 10 to the negative 9 coulombs, which gives us 65.7 picoamperes. If you notice, instead of going through all this, we could have just multiplied the incident current by the transmission coefficient to get the same amperes, but we just went through that method because that was just to explain how much charge the electron carries. The remaining part of the question says, what becomes of the remaining current? So we know that the remaining current, which is 1 milliamperes minus 65.7 picoamperes, is reflected at the layer.